Right, so here's a short clip on decay equations and how to solve them and know about them. So, two things that you need to remember for decay equations are the following. This symbol represents alpha, an alpha particle, and this symbol represents a beta particle. Make sure you memorize those because that's important for solving decay equations sometimes. So, let's look at alpha decay. So remember, some atoms are unstable and they will release radiation, either alpha, beta, or gamma. And this is what happens in a bit more detail. So we can see from this diagram, we've got a uranium nucleus, and it decays and releases 2 protons and 2 neutrons, which you know is alpha. So we know if the nucleus loses 2 protons and 2 neutrons, its mass must decrease. It also means we must lose 2 protons, because we lose 2 protons, 2 neutrons, and we must lose 2 neutrons. So that means because the atomic number is the number of protons, that decreases by 2, and because the mass number is the protons and neutrons added together, that decreases by 4. And that can be a definition you can use. A loss of 2 protons and 2 neutrons causing the atomic number to decrease by 2 and the mass number to decrease by 4. Now, you could be asked to solve these alpha decay equations. It's really simple. It's just like balancing equations. So the number on the left must equal the numbers on the right. So this is alpha because we've got a 4 and a 2 with a helium, which represents alpha. 232 on the left. 4 plus 228 will give us 232. And 2 plus 88 will give us 90. And that's why we've got those numbers there. Same here. 4 plus 212 will give us 216. And 2 plus 82 will give us 84. And then we've got this one. 4 plus 221 will give us 225. And 2 plus 87 will give us 89, which is why we've got these. That's the sort of question you could be given in your exam to fill in those gaps. Now this is beta. So a beta decay is when a nucleus releases a beta particle, and it does this because a neutron becomes a proton. Okay, it does this to make it more stable, because usually atoms are unstable because they have too many neutrons. So this makes it more stable by reducing the number of neutrons and increasing the number of protons. So hopefully you'll realize that the mass doesn't change at all, because an electron is so small, has so little mass, it doesn't affect it much. So we say it remains the same. The number of protons must increase because we've said a neutron turns into a proton. Okay? And then because a neutron turns into a proton, the number of neutrons will go down. Now, the atomic number is simply the number of protons. So because we're gaining an extra proton, it must increase by 1. And our mass number stays the same, because if our number of neutrons goes down, so say we had 10 protons and neutrons, if the number of neutrons goes down, the overall number of particles goes down to 9, but it turns into protons, it goes back up to 10 again. So the number remains as 10. So the mass number remains the same. Now, a good definition is a neutron turns into a proton, causing an electron to be released. That's a good definition of beta decay. Here's the same thing. We use the same as before, except this is beta decay, and we've got a 0 and a -1 with an E to represent beta. So we just do the same as before. We need to equal 14. So 0 plus 14 will give us 14, and -1 plus 7 will give us 6. And then we've got 0 plus 241 will give us 241, and -1 plus 95 will give us 94. And then we've got 0 plus 35 will give us 35, and -1 plus 17 will give us 16. And there are our answers. Now, gamma's easy. Everything stays the same because gamma has no mass. The nucleus of the unstable atom isn't losing anything. So everything stays and remains constant. And the numbers stay the same throughout. So you're unlikely to get a question like this in your exam. Okay, but if that's 0 and 0, it must be gamma. And the numbers just stay the same either side of there, because it's still 3 plus 0 gives us 3, and 2 plus 0 gives us 2. All right? And we can use that as the definition if we want. Rearrangement of protons and neutrons causing a release of energy in the form of a high frequency electromagnetic wave. Right, here are some examples. So we've got a 4 and a 2 here, so this must be alpha decay. We've got 0 minus 1 with an E on both of these, so these must be beta. And these are just the same as before. So we go 4 plus 180 gives us 184, and 2 plus 72 gives us the missing numbers there. And we just do the same for all the others. These are all the other answers. Okay, don't worry about these extensions ones here. Again, we could look at a beta one. We know it's beta because it's a 0 minus 1, number 7. 0 plus 14 gives us 14, and minus 1 plus 7 gives us 6. And these are all the answers. Please have a go at those without using the answers. Then we've got this. From chemistry, we should know that the mass number of an atom, okay, is the number of protons and neutrons. Beta decay does not cause the mass number of an atom to change. That's because, if we remember, beta is when the neutron turns into a proton. So if something has a mass number of 10, let's say, a neutron, the number of neutrons goes down by 1, so the mass number goes down to 9, but instantly the number of protons goes back up again, so it knocks it back to 10. So that's the reason why the mass number always stays the same with beta decay. So here it gives you the symbol for alpha, which is quite nice, and it asks us to complete. So this is the same as before. So we've got 208 plus 4 gives us 212, and then we've got 81 plus 2 gives us 83. Okay. It says it is impossible for alpha decay of bismuth 212 to choose the same element as the beta decay of bismuth 212. So if we take bismuth here, its original atomic number is 83. Now with alpha decay, that number will decrease by 2 because it loses 2 protons, so it go down to 81, and that will become a different element to 84, which is polonium. And that's what happens with beta decay, is the number of protons goes up. So these atomic numbers determine what the element is. So if these numbers are different, the element's different. And because alpha reduces the atomic number by 2, that's going to be 81, whereas this one goes up by 1, so it's 84. So they're going to be different elements. Now, let's look at this one. Here we've got a different symbol, but we know that's alpha because it says that symbol represents alpha. Plus it looks like a little a. So we can just replace the HE with that and put the 4 and a 2 there. And we just work it out the same as before. So 206 plus 4 gives us 210, and 82 plus 2 gives us 84. So Z is going to be 82 because 82 plus 2 gives us 84. And A is going to be 206 because 4 plus 206 gives us 210. And we do the same idea with here, but this is beta. So beta has a 0 and a minus 1 because it's the E with a 0 and minus 1. So then we have 89 plus 0 gives us 89. And then we've got 39, or minus 1 plus 39 gives us 38. Now, more on here. Really easy on this one. I don't need to go through this. So that's going to be 206 and 82. This one is alpha. So we've got to remember, because that's alpha, it looks like an A. We've got to remember that's a 4 and a 2. And then we just balance it. Okay, like so. And then we've got to fill these in. So we've got 139 and 139. Now this is tricky because it doesn't give you a huge amount of information, but we know if the mass number stays the same, that must be 0. Okay, so that means if that one's 0, it's going to be beta decay. So we know it's 0 minus 1. And then we know that if we've got 56 and we've got minus 1, we need to do 57 plus minus 1 will give us 56. Or minus 1 plus 57 gives us 56. And then finally, we've got this one, which is, these ones are a bit funny, a bit tricky. So a nucleus emits radiation. Figure 1 shows how the mass number and the atomic number change. So you can see here, D, the mass number goes from 226, 4, so it goes down by 4, and the atomic number, which is this one, goes down by 2. So the only one where the mass number goes down by 4 and the atomic number goes down by 2 from 88 to 86 is alpha, okay, which is just there. Then we look at the same thing here. Here we can see the mass number remains the same, okay? The mass number remains the same from 234E until there, 234, but the atomic number goes up by 1. So the one where the mass number remains the same, but the atomic number goes up by 1 is beta. Then, nucleus B decays by emitting an alpha particle. Draw an arrow on figure 2 to represent that. Okay, so alpha is a loss of 2 protons and 2 neutrons. So the mass number goes down by 4. So it goes from 226 to 222. That's why we got it to that point. And our atomic number goes down by 2. So it's gone from 88 to 86. So we draw the arrow down like that. And then finally, polonium-210 is radioactive isotope that decays by emitting alpha radiation. What is the correct decay equation? So we've just got to balance it. All right. 214 plus 4 doesn't give 210. So it's not that one. 206 plus 4 does give 210. 86 plus 2, okay, doesn't give us 84. So it can't be that one. 206 plus 4 gives us 210, and 82 plus 2 gives us that. So it must be that bottom one. Hopefully this makes sense. Thank you very much. To 224.